Okay, so this one is um Unit 3, Part 2. So we're going to continue to study physical and chemical properties of materials. So when you think about magnetism, we're just studying two ion-based materials. Okay, we call it ion because that's how we found out this phenomena. So they're just attracting, okay, to each other. So today we use ion-based materials, okay, and they have some sort of attraction in between them, and that's what we call it magnetism. So a long, long time ago in the ancient world, we discovered this magnetic behavior, and we use it in compass, okay? So compass, you have a little hand, and that hand is made of iron, okay, or iron-based material nowadays. So what happened to it is that, in a condition that you make, that hand is reacting to the magnet that we have in our planet, which is our world. So when you take a look at the Earth, you're going to see there is a magnetic core, okay? So it's North Pole and then the South Pole. So every magnetic material, the south, okay, pole of the magnetic material is completely attracted to the North Pole of the Earth. So you're going to see in your compass hand, the South Pole is always pointed to the north. Okay, why? Because it's been attracted to the North Pole of the planet. So the phenomenon of the South Pole of magnetic hand is attracted by the Earth's natural northern magnetic pole. We use that to make compass, and we use a compass to navigate. And then we discover a continent, okay? And differently, we can cross the oceans, okay? So that's a very powerful instrument human has ever developed. Okay, so when a material is applied by a magnetic field, okay, this is just a made field, and you want to subject that to a material. So what happened is we call the magnetic field strength as an H. Okay, that's just a symbol to describe this magnetic field strength H across the material. So magnetic flux, okay, with density, and we call that B. Okay, so that flux appears through the gap. Okay, so the magnetic properties, they're happening. The field is happening between the two ion-based material, and we're going to use that field with a strength H, and then we're going to apply that field to the material and see, like, what kind of reaction they do. So what happens is magnetic flux, okay, and we usually describe the flux with a density B, and that flux is gonna go through the gap, okay, and permeability is nothing but the magnetic field with a particular strength divided by the flux. It's just a ratio, okay? Ratio of field strength to flux density, and we call that permeability. So that flux persists after the field, okay? And if that flux is gone, we call that the remnant induction. First, we have the material. We're going to subject a magnetic field. We've got flux, and that flux is going to stay for a while. And we call the strength to flux ratio permeability. Okay, and the flux is going to be gone. Okay, uh, but it's going to stay a little bit. Okay, even if you take away this magnetic field. the flux is going to stay on. And that phenomenon, we call that remnant induction. Okay, it's kind of like a momentum after a particular movement. Okay, so you have a flux, and that is going to stay on after the the magnetic field is removed. Okay, you still have it just for a while, not forever. So here we can see the H. Okay, and it's going to go up to a certain level, that's just a flux, and it will come back down to another level, another flux. Okay, so when you take a look at it, these lines are forming a loop. Okay, first you go up to a level and then come back down. When it coming back down, it's not taking the same path. Okay, there's a gap. See that gap right over there? So you get a loop. Okay, this is just a graph describing that phenomena, which is magnetic field applied to a material. The flux is born. Okay, and then field, you can remove it. Okay, then flux is going to stay on a little bit. Okay, and then it's going to go back down. Yeah, forming some sort of a loop like that. And that's a magnetic property on the material, okay, by the magnetic field. So a complete cycle of the magnetization forms a loop. And that loop is not physical thing, okay? This is just a description of the magnetization happening to the material by a magnetic field, okay? So in order to lower the flux density to 0, we're going to use a little HC, and you will use that in opposite direction while we're getting a loop. Is first we've got the flux, and we have to lower that flux back to 0. So when we do that, we have this magnetic field strength. Okay, this much we call the HC. The first one is H. So HC is going to be used at the opposite direction. Okay, to the first original field with strength H. And we call this coercive magnetic force or coercive field. So on the graph, when we draw it, we can see that little loop, and we call that loop hysteresis loop. It's just the index of the energy lost or lost energy, okay? In that complete cycle of magnetization, you're subjecting a magnetic field to a material, okay? And the curve, we call it BH curve, your flux and strength curve. And that comes in different shapes, okay? The loop is different shapes. And the shape depends on, again, the magnetic material, okay? What material are being subjected. So the device we use, magnetization, is called electrical transformer. So when you look at the transformer core material, they have a very small area inside the hysteresis loop when you draw the graph, okay, of this material subjected by the magnetic field. We got the same loop, right? But that loop is really small. And the loop, as we already know, is a representation of the power loss, okay, per cycle. So we don't want to lose the power, so therefore we gotta keep it as low as possible, yeah? And lost energy gotta be kept as low as possible, therefore the area should always be small, yeah? So the material used for this purpose, we call it soft magnet because you can easily magnetize and also demagnetize, okay? Why? Because this material, the transformer material, they retain power. They didn't let the power loose, okay? So the power loss is very low. So therefore, you can see the hysteresis loop area is very, very small. So since you want to save the power, you use a transformer. Because if transformer is losing all the power that there's in the world, it won't be transforming the power, yes? So therefore, the transformer core material, okay, subjected to the magnetization or magnetic field is going to give you a very small hysteresis loop. Okay? Why? Because it's trying to retain the power. Computer disk. Okay, computer disk is where a particular structure and we use it to store data. Data is energy anyway. To store data. So in a computer disk, a sizable value of your flux, okay, got to be achieved. And the same value got to be retained when the power is off. So how are we going to structure the material so that, okay, this flux value is going to stay the same? Why? Because we want to retrieve the information later and we don't want to lose it. So a square loop, okay, meaning like the material being subjected by the magnetic field got to create a loop that is constant in size, okay? So therefore your BS and BR, right, that little first go up to a B and then come back down, so that's your BS and BR. So that gap got to be very, very close, okay? So therefore the hysteresis loop shape is going to stay the same, so you can be able to keep the data. So the power of magnet is related to, again, which is so important again and again, okay, the properties depend on the structure. The reaction depends on the structure. So the power of the magnet is related to the area within the hysteresis loop. Hysteresis loop is just it's happening on the graph, okay? It's just a representation of what's going on in physical material. So that is going on in physical material, which is the loop is formed, and we play with the loop size, okay? We want the loop area to be small in transformer. We want the loop, okay, to be square and maintain at that size in computer disk, okay? So now we are making the structure up in the way we want it, so we can use the property that comes with it to serve our need, okay? Permanent magnet is, when you take a look at the hysteresis loop, you're going to see that loop is really large, okay? And you can see it, you can see that kind of large loop in the magnetization of permanent magnet, okay? So material with its characteristic, and we're going to call it hard magnet like that. The ancient one, these are like a little sophisticated today's stuff, yeah? Optical, so we get into optics. So optical properties are different from electrical properties. So we're studying the properties of all the material that there's in the world. So these properties are just responses, okay, of the material again this time is light. Okay, how do the materials respond to light? They respond differently, yeah? They can emit, absorb, reflect, transmit, or refract the light. So let's go in here. Reflect. So you've got light, we have a lot of light rays from the sun, and they all shine on everything, okay, in this world, or the planet Earth. So when the light shines onto a very smooth surfaces, and we have all the surfaces that there is in the world, okay, in many of our objects, and our skin is a surface as well. So when the light shines on a smooth surface, okay, we have smooth surface, we have rough surface, yeah. So for smooth surface, nearly all the light is going to be reflected off the material, and they're going to reflect at the same angle, and we call that kind of reflection from the smooth surfaces specular reflection. That's just ability, okay, of the stuff to produce specular reflection, and we call that reflectivity. Yeah, reflection, reflectivity. Light shines on a smooth surface, reflect everything back at the same angle, nearly everything back. Okay, so when a light shines onto a raw surface, it's a different story. So the light is reflected in various directions. Why? Because when a surface is rough, Okay, when a surface is rough, you've got different surfaces. It's going to strike here, it's going to strike there, and then it's going to strike there, it's going to strike there. So therefore, the reflection is going to be different. Okay, so that's what we call that the reflection various directions going anyway. For the smooth surfaces, a straight, really smooth, okay, and just go, and then it's going to go in the same angle, yeah, like that way. So then you can put the arrow like this. It's the same thing. Smooth surface and rough surface. Metals, they have very high relative reflectivity. Okay. I forgot to mention the rough surface. Okay, the variously directed rays, we call them diffuse reflection. Okay, not specular reflection is for smooth surface, and diffuse reflection is for rough surfaces. So metals, when we think about the material metals, they've got very high reflectivity, and light cannot penetrate deep into the metal. Light can penetrate further into the glass. So if you think about the metal, okay, they love, because it's a smooth surface, so they love to reflect back, and they have very, very high reflectivity, and light cannot penetrate very deep, okay, into the metal. Okay, it can penetrate a little bit on the surface, but not so deep. But for glass, okay, light, so if this is glass, light can penetrate, okay, uh, into the glass farther. So the angle is a little bit, it's going to be not straight, it's going to be a little bit different, okay, like that. So when you think about the white light, so white light, they have color. So when we think about the white light, right, and I just told you they're composed of violet, blue, green. These are just the components of the light. And these components, they have a very particular phenomenon. It's because some of the components, they reflect according to the surface, okay, that they shine on. So some of the material reflect, some of the component. So it depends on what component some of the materials reflect. We name these colors, okay, and the colors come from how our eyes see the material. Okay, so if you see the yellow, right, you're gonna test another one, another yellow color, and then you're gonna check, all right, the white light component, and you're gonna see one of the component is consistently reflecting, and we call that component being reflected yellow, just because our eyes, okay, see the material surface yellow, okay, not because the component is yellow. No, we don't know how they look like, but in our eyes we see that color. Yes, so therefore we name it that way. Okay. Um, so different colors are seen when white light shines on the material. Not all the components are being reflected except for the black, right? Black body, and you have all absorption, and you also have all reflection. Okay. White light, you can say white because it has everything. It has everything. Okay. So if you think about the color, okay, black, you're seeing black because they absorb all of that. Okay, all of the violet, blue, green, yellow, and then the red light. Okay. So black object because they love to absorb the energy. So they absorb all the light components into it. So you see black. Therefore, we call the black body is energy absorber. Okay, and you can also absorb heat in a black body. Okay, so good for keeping heat inside. So anyway, the main point is different colors, okay, are seen when the white light shines on material, and some of the components, okay, one or more components are reflected back, so you see different colors. Alright, so the next one is emission. Emission is a different properties. So emission refers to like electromagnetic radiation. So electric, this is magnet, and there is radiation. Radiation means something coming out of a body, okay, or an object. So right now we're using the word material, so electromagnetic radiation from some materials. So emission is nothing but some of the material, okay, they emit. So meaning like electromagnetic, okay, field is going to propagate, okay, from that object through the space. Okay, this is space, and we call that nature emission. Okay, they just come off from the material by themselves. And what is coming out? Electromagnetic field. Okay, magnetic. When you think about magnet, it's always come with a field. Okay. So when you think about the characteristic, okay, of that type of radiation, they're related to all the lights we have ever known. Okay, so we go back to our electromagnetic spectrum. So our visible light is one of them, one of the component of that spectrum, and we have different colors. So here is a full color than previous slide. So we have indigo and violet, right? So then we have radio waves, and then we have microwaves, and then we have infrared, we have visible light, we have ultraviolet, and we have X-ray, and then we have gamma ray. So if you pay attention, okay, to the value, you see this is going smaller and smaller. That's really, really long wave, okay? So wave again, it's called wave because they come out of a source, okay? And source is electromagnetic, okay, source. It's just material, and you need like about two objects, okay, either in the universe or space, and they subject to each other, okay, or some sort of attraction like magnetic attraction. So every time they do that, you're going to see some sort of lines around them interacting, okay, and coming out like that. And like electricity electron is we're talking about mostly the electron particle, okay, so electromagnetic field is going to propagating from some objects or the material through the space, and we call that emission. So when you think about the wave, okay, when you think about the wave coming up, these are the different waves, okay, coming up from different sources. So students always forget about the source. So don't forget about electromagnetic radiation. They come from the source in the form of waves, okay? So if you think about radio wave source, try to remember the source, microwave, try to remember the source, infrared source, ultraviolet light source, not just the length of the wave, okay? Most of you try to memorize the length of the wave, but then forget about the source, where they come from, okay? Absorption is a complementary to your reflection. So when the light strikes on a material, some of the portion of that light, components of the light, is going to be absorbed. Okay, not everything is being reflected, nearly everything, but some portions are being absorbed into the material, and we call that absorption. Photoelectric effect is very important because when the light strikes certain materials, okay, the materials are again made of atoms, so we go all the way down to atom, atomic level, and you know the particles floating around in orbit, okay, we use the concentration or probability of finding electrons anyway, so particles are around there, so they get knocked off, okay, so electrons are emitted from the surface when the light strikes, okay, light can go straight into the atomic level, okay, they're very, very small penetrating light, so they go and disturb the orbits. So when they disturb the orbits, electron come off. Okay, and we call that photo, for your light, electric, your electrons from your atoms effect. Okay, so the material then becomes positively charged, meaning every time you lose, okay, negative, we call it negative. They don't exist. We call it positive or the leftover, which is hanging still there as photons, okay, and positive charge when you lack one of the particle in orbit. We call the electron, the particles in the orbit, electrons, and we call it negative. These are just the terms, okay? The reality is just their little parts, that's all. When the little parts come out, we call that condition positively charged. And then the emitted electrons we call them photoelectrons, okay? Because it's been knocked out by the light. So bang, and then come on, that's your photoelectron. Because it's been interacted, okay, interacted with the light. Again, a transfer of energy, transfer of heat. Heat is a transfer of energy. So bang. So with that, okay, collision and come on, bang. Okay. Sometimes you might knock the other electron off, but then that's just for the graduate study. The path is not always clear like that, but these guys are like concentrating. Probability of finding is everywhere. So the shield, okay, the nucleus can be shielded. You know, sometimes like you get a clear path like that. Sometimes you're gonna bump that, and then this one will come off instead of that. Okay, depends on the force. So you go back and apply your physics force again. Yeah. So material that can produce photoelectric effects, and we call them the alkalis or alkali metals or compounds. Yeah. And in the lab you play with it. In the lab you play with everything you've got. Yeah. And then you record which one is reacting or which one isn't. So at one point we found alkali they react, and they do this quite often. Yeah. Okay, luminescence. So some of the materials they emit visible light. Okay, and we call them they glow. So when exposed to especially your UV light, okay, UV is an ultraviolet light. So the materials are said to be fluorescent. Okay? But the entire phenomenon of glowing, okay, or emitting the visible light is called luminescence. Yeah, and fluorescence is we concentrate on material, okay, and the material they emit the visible light or they glow. But that happens when they're exposed to UV light. Okay, the entire phenomenon again is your luminescence. Material, or we call it fluorescence. Yeah, so don't forget phenomenon and material, luminescence and fluorescence. So some material they continue to glow even if you remove ultraviolet light, just like you remove the magnetic field and you still have your flux. Here you remove the ultraviolet light, you still have the glow. Yeah, and these materials we call that phosphorescence. Okay, continue to glow. Transmission just goes straight through. So some lights they can transmit through certain material, and that property is called transmission. If they cannot go through, okay, we're gonna have an issue. Living in dark houses, something like that, or you have to have an internal light. So now we use glass, right? Windows so important to make the house pleasant. So because it has ability to transmit, okay, the sunlight. So that property again going through certain material, okay, we call that transmission. So infrared light can penetrate, right? They can penetrate IF, your light, solids, and also transmit it through them. Okay, so that's pretty powerful light. And then semiconductors, I recovered from flu, but then I'm still struggling with talking. I need to rest a little bit. Give me a break. Alright, so the semiconductor, we call them semi, is because they are transparent to the infrared radiation, but then they're opaque to the visible light. Okay, so anyway, there are many different materials and many different types of transmission. Refraction is another property of light. Refraction is nothing but the light bands, okay, when they move from one medium to another. So when you put a stick in the water and you look that stick, okay, from above the water, and you're going to see the stick bends. So that's because the light refraction and the light refract back from the stick through the water back into your eyes. So the light ray, they move from air medium to water, so we vision them bend. And don't forget, just because we draw the two-dimensional, okay, light ray from the source through the medium and then another medium, and we draw these lines, and I'll show you later. But refraction, when we talk about refraction, how we observe the band, okay, it's not only that drawing, it's your eye, okay, looking that. So even though we draw it very simple, don't forget your eyes, okay, looking that. Alright, we're not going to get into the details. So refraction happens because the speed of light they're different in two media, okay? While the speed of light is different, light is just a physical thing. They're composed of very, very tiny particles, okay? And they can knock out other tiny particles, and they can go through some of the medium. So the medium, again, are composed of stuff anyway, right? Air is composed of air stuff. You have nitrogen, which is your inner gas, and you've got a lot of them inner gas, and then your oxygen, and your water vapor, very little, and then carbon, okay, dioxide, little stuff in there. So that's your air. So the light, this little, okay, particle ray is going to go through a medium composed of other molecules. And then when it moves, a different medium, water is bigger, yeah? Water molecules are bigger than the air. So, and when they're aggregated, you got ocean, river, stream, lake. So when you go in, when the light go into the other medium, then they have to put more in, they have to go through a different molecule. So therefore the speed changes, okay? Because they have to put more energy to go through water than it goes through air medium, okay? So in air is faster, and in water goes a little bit slower, yeah? So the angle of refraction is the angle between, okay, when they change that path, you got a different angle. That's all it's talking about. And a line perpendicular to the surface. So you have a one medium and coming like that, and you go into a different medium, and then it changes the direction, okay? A little bit, and we call that refraction. Why? Because of the stuff that is made up here, okay, and the stuff that is making up here, they're different, okay? And the light itself is particle, okay? So don't forget any of that. So therefore the angle is different. So I'm gonna erase this one so you can print. Alright, so now this is our two-dimensional or regular drawing. Incident ray, okay? Here is my first medium air, second water. Medium air is kind of white. That's because the material is they have more distance in between them. Okay, water is more compact. That's why you can see water and touch the water. Okay, and you have a physical water, you can see it. That's because the bond are closer and distance is closer. So therefore, when it strikes, okay, through the air and then hit the surface of the water and go into the water, it's gonna bend. Yeah. And the speed is different, okay, completely different speed. So you go with C, and then now we have a certain velocity. So that's what's showing right here. So speed of light in the vacuum, and then speed of light in the medium. We call it vacuum because it's not very different. You know, C and the speed of light in the air is not that different. They still maintain relatively very, very similar C, okay, from the universe and into here. Yeah, not much different. But the very intense, like intense, very strong, okay? Because the source of the energy that comes from the sun is like a burning, totally burning with incredible amount of fusion and fission going on right there. So that energy, the ray that comes out from that source is pretty intense, okay? You can't see it, but it's really intense. So here you still keep the C and then it changes to V, which is a different speed. And that constant, this little n, is just showing you the angle, right? We have my angle 1 and then I have my angle 2. Okay, so sine theta 1 and then we have sine theta 2. And when you study the sine theta 1 over sine theta 2, you're going to get a constant, and we call that the refractive constant, which is your little n right there, okay? That's the original path it's supposed to be. Here is showing you the medium changes. So the same thing that we use light to study the space climate. Okay, you shoot light here and there everywhere, and we're studying these angle changes, yeah, so that you can be able to understand the material that makes the universe. All right, chemical properties. So for chemical properties of material, we're looking at corrosion and then oxidation because they matter in our product. You know, we don't want our product to corrode. We don't want our product to be oxidized, okay, because they're going to damage their quality. So these are the measures that we, how the material they interact with our environment, okay, the earth environment. Corrosion is nothing but just a deterioration or destruction, okay, material because they react to the environment. So the environments are corrosive to everything, okay, in the world to some degree, because our environment is, we have humidity, we have salts in the water, we have steam, we're all subjected to it, okay, and then we have chlorine, ammonia, sulfur dioxide gas, we have acids and other solvents, okay, so all these things, okay, definitely enhance the deterioration of the material, which we call that corrosion, reaction to the environment. So how chemically active the material is, okay? So every time you think about the corrosion or corrosive property of the material, we look at the material, we check the structure of it, and we see if they're chemically active. Okay, active means it can react to the environment. And then the nature of surface, okay, their surface film. So surface film always they form, okay, when the material is subjected to the environment. And you've got to look at it, what kind of surface film, okay, formed to the environment to determine how corrosive, okay, resistant a material can be. So if the film that formed is not strong enough, okay, it can't be resistant to the corrosiveness, right? It will definitely corrode. So corrosion, they take place in many forms. So these are different types of corrosion. The very first one is they corrode uniformly. We call that uniform attack. It's just a general corrosion. So what's going on is you have a chemical or electrochemical reaction. Okay, that's usually happening on the exposed surface. Okay, galvanic corrosion is we have two. Okay, two different things. And here we're talking about metal, especially because most of our stuff are made of metals, and metals always going into corrosion. Okay, issue. So one metal is going to corrode faster. Okay, when you have two metals together. Okay, and they usually undergo pitting, meaning like forming cavities in some of the localized areas. So that's what we call that the galvanic corrosion. The next one is your intergranular corrosion. So intergranular corrosion that happens usually at the grain boundary. Okay, grain boundary is nothing but just a boundary. Okay, we are looking at certain material. In this case, is a stainless steel. So it happens only at the grain boundaries, and then it causes a failure in these material, okay? And we call that intergranular corrosion. Stress corrosive cracking is a result of accelerated corrosion. So meaning like that corrosion really fast. Why? Because it is caused by residual stress, okay, leftover stress. and that stress is in the metal or an externally applied stress coming from a particular chemical. Okay? And I'll show you how the stress corrosive cracking, it's just a cracking happen in the material because of the stress. Okay? Corrosive fatigue is kind of like the result when the corrosion is accelerated, okay, because of cyclic or repeated stress. Again, because of some stress, but that stress is again is repeated. That stress is coming in pattern, okay, cyclic, coming in regularly. So you have constant corrosion, and we call the material is in corrosion fatigue. Okay. Maybe the way that they put the thing is not right. That the certain material is subjected to regular stress. So we have uniform, we have galvanic with cavities, we have intergranular at the grain boundary, and we have stress corrosive. Cracking happen because of stress on the material, and corrosion happen because of the constant stress on the material. Okay. All right. The intergranular corrosion, if you go and make a real exaggerated picture, you're going to see like that. So at the boundary. So the stainless steel is pretty good because many of the designers use stainless steel material in many things. Okay, also expensive. So the common corrosive resistant, because we have to study the thing that we use most, right? So we study. So we have a common corrosive resistant industrial material because they are resistant pretty good to corrosion. That's why we choose this material. Okay, so the surface film of the stainless steel, and we call that the chromium oxide. Okay, and this film, the surface film, is made of a non-porous, meaning there's no pores, and they can completely adhere, okay, to the base metal tightly. So that's the reason why corrosion is resistant. Okay, so stainless steel contains some amounts of carbon. Some of the stainless steel, they have carbon. Okay, and we don't want carbon, but carbon messes up things. We want as low carbon as possible in stainless steel when you choose a material. So when the steel is heated, all right, to a sensitive temperature range, this is kind of your specification. So that carbon in the steel is going to precipitate out, come out, okay, at the grain boundary usually, because that's where the carbon release is happening, and we call that boundary grain boundary. And then they form, instead of oxide, okay, they form carbide. So instead of getting chromium oxide, you got chromium carbide on the surface boundary. Okay, so and this chromium carbide is going to get rid of chromium oxide surface film. Okay, replacing it. There is a different compound. So therefore, that's the original surface film material, and that is something else is forming. Okay, since something else is formed on what's supposed to be, you got the change in the structure, and we call that change in the structure intergranular corrosion. Okay, well, it doesn't belong. Like you have cancer, if you have like a tumor on your nose or something, instead of your DNA making a nose, now your DNA is making the nose with a tumor. Okay, so something like this. So thus the choice of the super low carbon stainless steel is got to be the correct choice, yeah, not to get this kind of corrosion to mess up with your product quality. So stress corrosion cracking is just a cracking. So let's see how this crack happens. So in the presence of specific chemical and material, they're gonna fail, okay, even at a lower stress. Stress is nothing but just a force, okay, force or a reaction of some sort. Then its yield strength due to stress corrosion cracking. So no corrosion appears over most of the material surface. When you look at the material surface, you see that nothing is going on, right? In this type of corrosion, because the corrosion that is going on inside. So the fine cracks, they're going to develop through the material, right? So this is a more pretty serious issue. So the cracking can cause failure without any warning, but you can see it from the outside. So these cracks appear because of a specific material chemical medium condition. Okay, so stainless steel material chemical is your strength. So stainless steel example, so we go back, they produce crack too, okay, and if they are exposed to chloride medium, okay, so brass and ammonia medium, they usually also give this kind of cracking. So you don't want brass and ammonia, you don't want stainless steel and chloride, okay. So chloride medium, that is familiar to us as our water tap, right? So water, our shower water, used water, all the water in the house is subjected to chlorine. So from chlorine, you always get chloride in form somewhere. And that's why we get hot water and you don't want to drink it, okay? You definitely don't want to cook with it. And you don't want to take shower a long time either. Okay, that's for we put the chlorine that form the chloride in the pipe and things like that mess up for the bacteria, because bacteria always accumulate, fungus accumulate all the time in these humid area. So while we're protecting ourselves from bacteria, we're also subjecting ourselves with horrible stuff. Yeah. Oxidation is another reaction in chemical properties. So this is oxidation is between the metal and oxide. So metal form oxide by reacting with oxygen, okay, and that's happened without the water. But then people always, for some reason, putting water for oxidation and then mess up with the rust, okay. Rust is also a form of oxidation. Also, they go into corrosion as well. And again, it depends on the material. So it's a special form of corrosion is oxidation. So nearly every metal and alloy, they react with oxygen at a higher temperature, okay? So in room temperature, even if the metal is attached with oxygen in the air, they're not going to show that reaction to you. But if you increase the temperature, you're definitely getting that reaction, which is your oxidation. So when exposed to high temperature metals, they develop a very thick oxide film, okay, from oxidation reaction, and we call that scale, okay. In catastrophic oxidation, some of the metals scale, that little film that happens between the metal and the oxygen in oxidation, they can react with gases, and then they create a very low melting point liquid, okay. And that liquid, it can provide rapid transport of oxygen to the metal surface, bringing the oxygen faster to the metal surface. So they react. So therefore, accelerates the normal oxidation. Then that type of oxidation, we call that the catastrophic oxidation. That's why you always feel like there's water with it. It isn't the water. It's just a low melting point liquid, okay? And they're usually coming out from that metal scale reacting with the gases, okay? Internal oxidation. So that's, again, like you're cracking in the steel happening inside. So this type of oxidation, oxygen, they dissolve. Oxygen can dissolve, right? And they dissolve in the metals and then migrate inward and then form the outside particle inside of the material, okay? So a and that happen, the oxygen, they usually dissolve at a very high temperature. Okay, when they dissolve, they go into the metal and then mess up inside by forming outside particle inside. So the oxygen, they tend to react with first alloy, because alloys are just mixed metals, and then they cause hardening, and we call that brittleness, okay? Alright, so this is the end of part 2 and the end of unit 3.